Here are solutions to homework set number 7 for ECE 111. This homework is looking at capacitors. Capacitors act as integrators. So if I have this problem, I've got a circuit, this is the current going to the capacitor. What's the voltage? Well, again, kind of one way to think about this, if this is your bank balance, if I start at $0, which is typical for students, if I do nothing, I should owe $0 after 1 day. If I start adding money, the area under the curve is my balance. So here the area is 1/2 base times height. This area is 1. So my balance goes up to 1. Right here, the area is about 1/2. So it goes up another 1/2. Then, because here's the 0 line, it goes down negative by 1/2. I withdraw $2. Again, the area is -2, so I drop down 2. I withdraw another $2. Area is -2. Go down another 2, about -1/2. Then I start adding. Goes up 1/2. Right here, it goes up about 3. So 1, 2, 3. Wind up right here. Now the area is 1/2 base times height. 2.5, 2.5. And then I stop depositing money. Banks aren't supposed to lose your money. They hold on to it, so your balance stays constant. Same thing with the capacitor. Capacitors integrate. If it's the current, I'm charging up the capacitor, I'm discharging the capacitor, I'm charging the capacitor, and then it holds the voltage constant. That's a feature of capacitors. They bite. If you see capacitors sitting in the lab, these are the really big ones, the size of a can of Coke. Don't stick your tongue across it because it could be charged, could give you a little kind of a shock. What technicians oftentimes do is they carry a screwdriver in their pocket, and if you see a capacitor sitting around, put the screwdriver across the leads of the capacitor. That way it shorts across the screwdriver, not across you. So anyway, that's what it should look like. Problem 2 through 5 looks at if I have the same circuit we had last week, or a couple weeks ago, but now add a capacitor at each node. How does that behave? Well, previously, if I have a 10-volt source, say this is a step input, the voltages would be constant. With a capacitor, what happens is initially, assuming these are all discharged, say 0 volts, 0 volts, 0 volts, when this jumps to 10 volts, I now have all these currents are 0, but I have current flowing in. That current has no place to go, so it charges up the capacitor, and the voltage on V1 increases. When V1 increases, it then charges up V2, and V2 increases, which then charges V3, V4, V5. And here's what that looks like. Here's MATLAB simulation, kind of showing what's happening. If I can find it. Where are you? Here you are. So this is something we're going to look at in just a little bit. This is a simulation showing that 10-stage circuit. So initially the voltages are all 0. I raise the voltage on the left to 10 volts. That charges up node 1. That charges up node 2, charges up node 3, and so on. What I get is a first-order coupled differential equation, or 10 first-order coupled differential equations. That's how it behaves. Can I come up with the mathematics that describe that? And then if I let it run for a little bit, it's going to run for 5 seconds. So here's 3 seconds, 4 seconds. This is almost the steady state solution. That's what we calculated last week. Get rid of the capacitors. That's the steady state voltage. At steady state, the voltages are constant, so the derivative of the voltage is 0. The capacitors aren't charging or discharging. If I plot the voltage versus time, here's what it looks like. So initially the voltage went to 10. That's at node 0. That charges up node 1. That charges node 2, charges node 3, and so on. How do I come up with those equations? Well, we can do it like so. At any given node, like node 1, let's erase all this. Previously we said at equilibrium, the current from the node has to add to 0. We're going to do a little bit different now, because now I have a capacitor. The excess current charges up the capacitor, and the basic equation is I equals C dV dt. So V1 dot is equal to I1. Call that I1. From current in equals current out, I1 is a current from the left, current up, current from the right. So that's equal to C times V1 dot, I should put a C out in front. C dV dt is the current. That's equal to the current from the left, which is V0 minus V1 over 10, plus the current from the bottom, plus 0 minus V1 over 500, plus the current from the right, V2 minus V1 over 10. So that's the equation at V1. If I then simplify, group all the terms, divide everything by 0.012, I get this equation. And these numbers are really what I'm looking for. The 8.33, 16.833, 8.33. By symmetry, the same thing that happens at node 1 happens at node 2. I've got 10 ohm, 10 ohm, 500 ohms, 0.012. Same thing at node 8, same thing at node 9. So these numbers repeat at nodes 2, 3, and 4. Just increase the indices. The oddball is node 10. At node 10, there is no resistor to the right, so this term goes away. And I just have two terms. When I simplify, I get V9 over 10 divided by 0.012, gives you this number, and 1/10 plus 1 over 500 divided by 0.012 gives you minus 8.5. So these are the differential equations that describe the circuit. This is also known as the heat equation. If I have a metal bar, raise the temperature on the left, watch the heat propagate through, it'll satisfy the same differential equation. Basically, coupled first-order differential equations are the heat equation. To simulate that, well, to solve, if you stay tuned, you're going to solve problems like this when you get to circuits 1, circuits 2, and signals and systems. For this class, we can solve using MATLAB. And that's the beauty of MATLAB. If I can tell you the differential equations, that's these guys right here, I can solve using numerical methods. The trick is I first have to know what the voltages are, and I'm going to assume everything's at 0. V0 is 10. I can then calculate, once I know the voltages, what's the change in voltage. So this guy right here, that's actually dV dt, or the derivative. That doesn't really represent well in MATLAB, so I just call it dV, the derivative of voltage, at node 1, 2, 3, and so on. Once I've got the derivative, I can integrate. For example, if I'm at 3 meters, right here, and I'm moving at 2 meters per second, so I'm currently at 3 meters, in 10 milliseconds, I'm going to be 2 meters per second times 10 milliseconds. That's going to be 0.02 meters to the right of wherever I started. So it's the new voltage will be the old voltage plus how fast I'm moving times 10 milliseconds. That calculates the voltage 10 milliseconds later, then repeat. Move forward 10 milliseconds, then repeat. Move forward 10 milliseconds, keep repeating. And here's what you get. Same thing we had before. Right here. So here's my simulation. The important thing are these numbers. I can then run the simulation and show initially the voltage is 10. That charges up node 1 very quickly. That charges node 2. That charges node 3, and so on. So there, we just solved a 10th order system, or 10 coupled first order differential equations. Again, kind of hard to do by hand, but this is what's really nice about numerical methods. It's really not that hard. If I change the system, I just change these numbers. The algorithm stays almost identical. So that's one way to solve. And we'll let this go to 5 seconds. And then at the end, it saves the voltages and then plots them. So there's the voltages versus time. A second way to get this graph right here is to use CircuitLab. did that. And circuit lab, if I draw the circuit out to 10 nodes, well, I only drew it to 5 nodes because I got bored, but take it out to 10 nodes. Here the input, this needs to be a step function. What the step does, it was 0 for t less than 0, and then 10 volts for t greater than 0. If I just use a 10 volt source, that just gives me the steady state response, so I need to use this symbol. Given this symbol, then plot the voltages. This is what I get. So this is your V0. No, V0 is not shown. V0 would be a step that goes up like this. There's V0. Here's node 1, 2, 3, 4, 5. And there is no 6, 7, 8, 9, 10 because I didn't include them. But same solution. When you do a transient response in Simulink or in Circuit Lab, that's exactly what we just did in MATLAB. Come up with the dynamics and then integrate. Okay, so that was kind of fun. Next topic, we're going to look at a thing called eigenvalues and eigenvectors. Now, when you take Math 129, they're going to talk about eigenvalues, eigenvectors, and the explanation given is if I take the determinant of A minus lambda I, set that equal to 0, that gives me the eigenvalues. If I say A times the eigenvector is equal to the eigenvalue times the eigenvector, that's the eigenvector. Okay, so that's all peachy keen. What does it mean? Well, one problem in Math 129 is they have to make it generic. Everybody takes Math 129, engineers, mechanical, electrical, industrial, soil science majors, business majors. It's got to be fairly generic, which makes it kind of hard to give examples. Well, in this class, we can favor electrical engineering because this is ECE 111. Let's give an example using a circuit, basically the 10-stage RC circuit. If I put this in matrix form, I've got your x dot is equal to A times x, or probably more accurately, V dot is A times V. V are the voltages. V dot is how they change. And if you notice, back on these equations, now let's go this way. With these equations, the derivative at node 8 is minus 16.833 times V8. The derivative at V5 is minus 16.833 times V5. This is diagonal. The off-diagonal terms are 8.33. The diagonal is minus 16.83, except for this oddball, element 1010. I can do that in MATLAB. What this means is I have 10 states. A is a 10 by 10 matrix, and here's your 10 by 1. A is going to look like this. It's going to be diagonal minus 16.8333, saying at node 3, B3 dot is minus 16.833 B3, plus 8.33 times the neighbors. That's a 10 by 10 matrix. I could put that in by hand, or since almost everything is 0, I can start out with a zeros matrix, and then in a for loop. As I go along the diagonal, each element is minus 16.833. The off-diagonal terms are 8.33. And the last element right here, I've got to input by hand. Element 1010 is minus 8.5. So there's your A matrix. Now in MATLAB, you can calculate eigenvalues. So if we go over to MATLAB, here we are. I input my 10 by 10 matrix. If I now say EIG of A, that tells me the eigenvalues. That's what you do in Math 129. The determinant A minus lambda I equals 0. Much easier way of doing it. Eigenvalues tell you how it behaves. Something decays as e to the minus 32t. Something decays as e to the minus 0.35t. And there's actually 10 different modes. That's an eigenvalue. Eigenvalues are important because if I look at the slowest one, this guy right here, that tells me how long it takes to get to steady state. Roughly, 4 over the pole is your settling time. So it's going to take right around, what's that? 4 divided by 0.3531. It takes about 11 seconds for this to settle out. So if I take the circuit, charge it up, I've got to wait 11 seconds to get to steady state. That's what the eigenvalue tells you. Eigenvectors tell you what behaves that way. Now, not very many people understand eigenvectors. If I just type in EIG, that gives you the eigenvalues. Those are fairly common. The slowest fold tells you how long it takes to settle out. 4 over the real part is your settling time. The eigenvectors, very few people understand eigenvectors. If you return two numbers, I get both the eigenvector and the eigenvalue. What the eigenvector tells you is what behaves that way. Eigenvalue tells you how it behaves. So something decays quickly. This is what decays quickly. Something decays slowly. Bring it over here. Here's the slow mode. Behind that image. There's the slow mode. This is what decays slowly. And all the modes in between. So, to illustrate what that does, let's pull off the fast eigenvector. If I say V0 is m of colon comma 1, this says take all rows, first column. There's the fast eigenvector. And let's scale that by 20, just so this goes about plus minus 10. Minus times 22. Okay, there. It goes plus about minus 10 as the initial value. I'm going to copy that. Go over here in my simulation. Instead of making the initial condition 0, I'll make that the fast eigenvector. And let's make the forcing function 0. So I'm just looking at the natural response. If I do that, just run it for 1 second. And I'm also going to change the limit to go from minus 10 to plus 10, just scaling what we see. Okay, so let's see what happens. If my initial condition is the fast eigenvector, we'll bring this over. Okay, you ready? Marks, get set, go. Poof. That was it. This mode decays as e to the minus 39t. It disappeared really quick. And you can see that if you look at the response, all the values decay as e to the minus 39t, and roughly 0.1 second, they're all gone. If I slow it down a little bit, and let's just do this for like 0.2 seconds, this makes the simulation run 10 times slower. The shape stays the same. The shape is the eigenvector. The amplitude is the eigenvalue. The amplitude is dropping as e to the minus 39t with the same shape. That's the fast mode. There's a second mode. This is the second slowest, fastest eigenvector. And this decays as e to the minus 30t. So that's got a weird shape. It decays a little bit slower. But notice the shape stays the same. It's just scaled in amplitude. The amplitude is the eigenvalue. The shape is the eigenvector. So those are the fast modes. Let's do the slow mode. The slow mode is just positive, so it scales a little bit better if I just go 0 to 10. Let's take the 10th mode. That's the slow eigenvector, and speed that up. Let's plot this for 2 seconds, let's say. If I let it go, marks get set, go. There's the shape. The shape is the eigenvector. That's decaying as e to the minus 0.35t. The slow mode. And there's actually 10 modes. There's 10 eigenvalues, 10 eigenvectors. The extremes kind of make sense to me. If I go plus minus, plus minus, plus minus, the voltages quickly cancel. That's the fast mode. If I go this shape, that slowly decays. Okay, so here's a question for you. Suppose my initial condition is random. We'll try that. I've got 10 random voltages with valid MATLAB code. What's going to happen? This is the last problem on the homework. Try it. That's what happens. So it started out random, and then This shape I recognize. That's the slow eigenvector. And that isn't just chance. That always happens. So let's try it again. Use a different set of random initial conditions. Marks, get set, go. It starts out erratic and then very quickly converges to the slow eigenvector. With random initial conditions, I've excited all 10 eigenvectors. The fast modes decay quickly, leaving the slow mode. This is called the dominant mode. What you're seeing is actually an eigenvector. After all the fast modes go away, what I see is the slow mode, the slow eigenvector. So again, this may or may not make sense to you. First time's always the hardest. We're kind of covering this because, again, very few people understand eigenvalues, very few people understand eigenvectors. This is kind of what they mean. So when you get to Math 129, linear algebra, and they talk about eigenvalues, think about amplitude. The eigenvalue tells you how it behaves. When they talk eigenvectors, think shape. The shape is the eigenvector. In this case, we go plus minus plus minus. That shape has a fast mode. It quickly decays. This shape that you're seeing right here is the slow mode. It slowly decays. And that is homework set number 7 for ECE 111. Again, some of the concepts probably you're not real comfortable with. That's okay. The emphasis in this class is getting used to MATLAB and exposing you to stuff you're going to see later on so that hopefully the second time you see it, it makes more sense. Homework set number 7.